Hello. Hello.
Hello, sir.
Yeah, hi. So you can hear me?
Yes.
Yes, sir.
So, yeah. So before I start today's class, tell me, do you have any questions, doubts of things that was done till now? I'm sure many of you have doubts regarding this P, NP and all of that. That I will cover in today's class. But other than that, on the dynamic programming part or something like that.
Sir, in the last tutorial,
Hmm.
there was an interesting code that was presented for a dynamic implementation of a recursion.
Mhm.
There, a simple line was added in the regular recursion code. And the claim was that that line would make it a dynamic program. And the line was simply like, if we think about filling up that a kind of a matrix,
Right.
when we're trying to store our values,
Mhm.
instead of going bottom up like in Bellman-Ford's algorithm, we just look at whatever quantity we want and what all quantities it requires, and we just
Yeah.
call them regularly in the recursion sense. But
Mhm.
every single time we calculate something, we store its value there, and
Right.
if it's already so let's say what the function was, it's just f of a, and it's calling on, let's say, f of a minus 1 and f of a minus 2 or something like that,
Mhm.
or f of p of a, where p of a is just some value lesser than a.
Correct.
So if f of a is calling f of a minus 1 and f of p of a, that was the example.
Right.
In this case, what we were doing was simply to calculate f of a, we were firstly seeing if f of a is already present.
Mhm.
So is it non-null? If it is non-null, then just output whatever it is.
Right.
And if it is null, then calculate it as the minimum of f of p of a and f of a minus 1 or something like that.
Right.
So just adding this clause of if it is already present, then just pick its value. And if it's not present, then calculate it. Isn't that always going to make a recursion algorithm a dynamic algorithm?
No. That will depend upon some many times the dynamic things. Okay, so it goes depends on the problem. Okay, a particular say a Bellman-Ford or Dijkstra kind of stuff like you can think of. Okay,
Okay.
where it can be updated again and again. Okay, it's possible that you are filling it up, right? So f of a has got filled up with something. But that's not the final solution of f of a. Okay, so it depends on the problem.
So, but if we look at Bellman-Ford, and here the value in every single grid of this matrix, let's just say it is f of I comma j.
Right.
I comma j is the I comma jth entry of the matrix.
Mhm.
Then f of I comma j.
So I mean, see, it all depends upon what you are storing. Okay, if you can prove, or if you are storing the value. So if you are at any point of time, if you are writing f of a, if something is stored there, then that is actually the value.
Right.
Okay, then yeah, of course, output that, and that's exactly how the code will be done. But if it is already stored, it is contains the value.
So in Bellman-Ford, that would be the case, right?
It depends upon, yeah, maybe in Bellman-Ford that can be the case, but then there are certain other cases where that might not be the case.
So actually, I'm confused. Where, like, can you give an example where that might not be the case? Because all the algorithms that we've seen till now, I feel we can do it this way. All we need to do is just store the values once it's first calculated. And if the recursion sequence is recursion, if in the recursion, what we're doing is sequentially calculating everything, all we need to do is just
like in the Dijkstra setting, right? At any point of time, you are calculating the shortest distance between I mean, you're trying to compute what is the shortest path that we know of right now.
Okay.
right? But
Right.
that no of right now can change, right? Or even so in the Bellman-Ford also, let me see. So in Bellman-Ford, you are storing the shortest distance between U and V,
Right.
right? That uses that uses some V1 to Vi, right?
Right.
Now, so if you think of the, so if you are trying to solve Bellman-Ford on the same rectangle where you are reusing the space,
Right.
okay? So you can see the same element is being updated again and again. The main idea is that after the ith iteration, right, the
Yeah.
shortest path between U and V using A1 to AI is stored.
So that wasn't Bellman-Ford, that was Floyd-Watterson.
Okay, that's Floyd-Watterson. Sorry. So I myself forget what is Bellman-Ford.
So the Bellman-Ford was simply a recursion on the shortest path from U to V using k many edges or something like that. Or you like restricting the number of edges that we could use.
Okay, so using k many edges, right? Okay, fine, good. Using k many edges
Right.
with 2 to the power k thing, right? Yeah. Okay.
No, sir. No 2 to the power k thing was there. That was repeated squares.
Okay, fine. Within k things, right? So now question is that thing is getting updated, right?
Right.
Using k things, then this k plus 1 and so on and so forth.
Right.
Right. So at any point of time, you cannot just pick up I mean, as soon as a square is filled, you cannot say that, okay, this is the shortest path between U and V.
Right.
Right.
But any square will output the shortest path between U and V using k many edges, right?
Using k many edges. I mean, that is after you are done with the whole thing, right? That's what I'm trying to point out.
So, but we figured out a recursion. We figured out a recursion equation.
Right.
And we know that anything that satisfies this recursion equation says that it also satisfies the boundary conditions that are known. That will be a viable solution for this problem, right? So instead of just calling it, so let's say we want to find the value of f of I comma j, and we know it has to be the minimum of f of I comma j minus 1 and f of I minus 1 comma j.
See, I mean, what I'm trying to say is that, see, like, so forget Bellman-Ford, okay? So think of this this Floyd-Watterson thing, okay? So this is a dynamic programming technique, right?
Okay.
But the issue is that there this rectangle is getting updated. After
Right.
ith round, what is stored in the point in a square UV is the shortest path going from U to V using vertices V1 to Vm.
Right.
Right. Now,
Yes.
now if somebody, if you want to say that, okay, at any point of time, if I ask you what is the shortest path between U and V, between V1 to Vi, okay,
Yes,
you
sir.
look at the so if you finish the ith round and then look at it, then that's perfectly fine, right? But if you
Okay.
don't, right, you will find that there's something already stored in the UV UV square,
Right.
and you will not update it in that case in your argument.
So, but why would UV already be filled with something that was an incorrect value?
Because it is left over from the I minus 1th order, I minus 1th iteration.
So, but in the I minus 1 iteration, so I minus
I mean,
1.
you might be reusing space, right? After I minus 1th iteration, every the UV coordinate contains the shortest path between U and V using V1 to Vi minus 1. Right. Now you're
Okay.
updating this. And you're not updating it by using a new set of spaces. You're updating it right there.
Okay. Right. Okay. Yeah. Understood.
Okay. In that
Right.
case, you have
Because
to
we're not using a 3D matrix. We're using a
2D
single
matrix.
matrix
Yeah.
and just keep on updating. Okay. Right. So if we are using something, if in this dynamic implementation, we have a static matrix. So in the Bellman Ford, we had a static matrix. We only updated every single.
Again, as
grid
I tell you,
just
so
once.
there is no trick like that. Okay. So that's the trick that you can see, but whatever you do it depends on the problem. In that problem, if that is working, that's perfectly fine.
Okay. Right. So I was trying to give a characterization to which problems when we can definitely do it, and those problems will be where in the dynamic implementation we are only updating a grid maximum once. If we're not revisiting a grid,
Then
so
you're
like
fine.
in the Bellman Fords, we don't visit the same grid twice.
Right. If you don't
So
visit
there we can do
anything
this.
once, then you can do that.
Okay.
But in that case, almost always, whenever you are looking for UV, it will not be filled to start with.
Right. Actually, this clause just makes it more efficient than filling up the whole matrix. We end up only filling up those grids which are required to find out the final answer, right?
No.
So something like, let's say,
That is in some sense the main. I mean, you can do that to some level. I agree. Okay, but that's a bit of a. Yeah, that analysis is much more complicated, I must say.
okay, I hope I'm not digressing too much, but if we look at that algorithm we had talked about, which was the longest common subsequence.
Yeah, because that one was just, I mean, it did depend on two things. If f of I depends on f of j and f of k, where k and j are something less than I,
right?
Then this argument that you're talking about, that would be exponential time. It will be just become recursive algorithm.
So, but what we're doing is once we've updated a cell, we are not going to calculate it again because it already contains the value, and we're just going to pick up that value using this clause. So we won't actually be recalculating any single cell using this clause.
Hold on. Maybe I should share it. I think this is actually the main difference between a DP and a non-DP. Okay. So say I have this whole thing. Okay. This is the cell that I want to say. I want to store it here. I want to know what is its value.
Right.
Okay. So the f of n.
Right.
You go there and say, oh no, f of n is actually, maybe you have to look at the factors of it. Okay. If n is equals to p times q, then you have to look at f of p. Not f of p, but I mean, yeah, what is stored in the pth cell and what is stored in the qs cell.
Right.
You say, oh, see, this is not filled up.
Right.
So I look at these two cells. Now these two cells are not also filled up. Then I go to some other two cells.
Right.
Okay.
Yes, sir.
And so this one will say that go to this one will also say this one, and this one.
Okay.
Now, thing will happen is that when you are dealing with this set,
right.
Okay,
right.
I mean, it is true that it is not be too bad compared to the actual thing, but this is more tricky. Because see, at this point, you have already looked into n.
Okay.
Not done anything.
Right.
Because P and Q have not been done yet.
Right.
Right.
Yes, sir.
Now you have gone into P and Q and you have not done anything because you are looking at the previous two things. They have not been done. So at some point of time, you will have to again come back to P.
When we've achieved all the pre-requirements.
So now question is that you have this prerequisite. So you are visiting one cell more than once. In fact, you have to prove that you have not visiting one cell more constant number of times.
So, but then calling some requirements from earlier, doesn't that just take, like, we won't actually be visiting P multiple times, right? We will just require, so let's say P
You have to
is,
prove it, right? Yes, you can do that. Okay, so this is a possibility. It is slightly better than recursive. It is actually it's quite good, better than recursive. But just
Right.
because, just by putting that clause, it doesn't take care of the whole thing.
Okay.
Let's put it this way. Then it depends on how you are traversing this whole thing. So because you continue like this, and you finally say, oh, this one value I have to first solve. Okay, let's solve this value. I have solved it.
Okay.
But now, how do I know where did they come from?
No, but sir, what I think he's trying to ask is, there is a very fixed way of in which a computer will process this. Like, let us say, if I for n I'm requiring
Just
p
one
and
thing.
q.
Just one thing. Yeah. Tell me. Yeah.
So let's say f of n is,
Yes.
let's say f of p plus f of q for time being. Let's say,
Yes.
okay. So f of n is f of p plus f of q. F of p gets called first. So it goes and searches like in a DFS fashion. Like f of p will be explored, like in the call stack, the function call stack.
So it will
It
be
is
like
built-
this. Okay, so you have f of n over here. N will say that I need both of them, p and q.
Yes. And,
P and q, then you go to p,
yes.
right? Or do you go to both? You have to
No,
say
no,
where.
no. You go FP and you go deep, like you go like DFS, like as DFS.
Okay, if you go off to DFS completely,
Yes, sir.
okay, so then you are actually revisiting this whole path, right? Yes, so that
Yes,
is
I
another
will
way
be-
of proving.
Yes,
Yes.
this will revisit the path. But the point is, if this particular, let's say the base, the leaf,
Yes.
once we hit the leaf and that value is saved, that value will be for access. It can be accessed in one time. So we will not be we don't have to recalculate.
That is true. So you are saying that. So the total number of nodes,
yes,
is anyways less than say n or something, right?
Yes,
and
sir.
you are going to traverse this one
in the DFS fashion. So it will be of order On plus n. Like, what I'm trying to say is, this will still be it will not be very bad. It will still be linear.
It will still be linear.
So I'm
That I
trying to
completely
make
yes.
I'm trying to make that point, because this is how I think call stacks work. Like they
yes. No, you are completely right. So that's what I didn't want to go in this direction, but I told you it can be done, but then you have to argue this whole thing.
Yes.
Okay, so this will be in order of n plus the depth of the tree, which can't be more than n, right? Because
no, it will be order of n, meaning it's not order n. It will be order plus so number of edges, right? Now what is the number of edges?
Yeah, right.
But since I'm assuming that every point is using two things, right?
Okay.
So the number of edges is also say 2n, right?
Okay.
So therefore the number of edges is also 2n.
Right, but it is some linear of what number of vertices.
Right. So it is really linear of number of vertices. So the total. So if you do this one in the DFS, you kind of traverse the graph in DFS form. Actually, not DFS. It's the inverse. Yeah, I mean.
I mean, I'm trying to give the way of,
or maybe you can think of this one as a topological sort, basically.
Yes. Something like
okay, it's like so these things should be done first, then it should be done this one, then this one, so that we can fill up. So you can think of these, all the edges are like.
So my main objective is to avoid recalculation.
Yes, so main objective is to avoid recalculation and also to not visit a edge or node way number of times.
Correct. So I have to traverse efficiently.
You have to traverse efficiently so that whenever I am there, I should be having all my sub problems already calculated.
Yes, right. That is what I'm trying.
And this will take an order of it's a linear time, so order n steps.
It will be linear time, so it will not be very bad. Like, I mean, this modification to recursion,
right.
I mean, it will not be very bad.
Yes, it will not be very bad. Yeah.
So one interesting order to calculate this is the topological order that you're suggesting, and what we typically do in the dynamic problem, approach is to calculate it in decreasing order of their distances from f of n, right?
in some sense, in the dynamic thing, what you do is that you don't try to optimize this thing. Okay, I mean, at least how I presented it, you don't. So you make, so here you are making a difference thing between this chunk, or maybe I should not write it n. So the number of nodes is m, okay, which is of course less than n. Okay, so number of edges is twice m. So if the number of nodes is very small compared to the n that I'm trying to calculate, this algorithm is faster than DP.
Okay, right.
Okay, but if this m is much bigger than m, it's kind of similar to n, then
Then DP is okay.
DP is as good as it. Okay, so in DP you don't try to optimize here.
Right.
Okay, I mean in general. Okay, the
Got
idea is that use it here.
We're assuming that M and N are
Yes.
not that far apart.
Yes, we are assuming that m and n are not that far apart. Yeah.
Okay.
Yeah,
And sir, I was just saying that in this case, we made a topological order of this tree, which was constructed out of the bare minimum nodes that we want to calculate.
Right. Yes.
And in the DP sense, what we will be doing is looking
we don't even think about this. It's a
Okay, there is
topological
no
sort of
tree
the whole
structure.
thing. The topology is sort of the whole thing.
Okay. Right. There is no tree structure actually.
There is no tree structure as such. I mean, we
Okay.
kind of traverse the whole set of nodes in such a way that whenever I'm going to update one, I have the rest of them available.
Okay. Right. So it's like if we have some sort of a tree, we are just starting from the leaf nodes.
Yes.
So
Yes,
we're going in
yes.
the reverse order of the generations.
In some sense, you can think of it. Yeah.
Okay.
मतलब level wise जा रहे हैं हम लोग.
Yeah.
Right. So that is like in the BFS sense then, right? Because
No,
then,
no. It's the DFS thing, not
No.
BFS, not the left. Think of it. It's the topological sort. I mean, we have to do it in the topological sorting function.
Okay.
I mean, not topological. There can be multiple topological sorts, but you have to do it one topological sort thing. See,
So
the
but then the
age
topological, sorry.
is basically saying that you should solve this node before you solve this. Right.
Right.
Or this node before you solve this.
Yes.
Right. Now question is that how will you do it? Do
Right,
it in any
topological
order you
sort.
want, such that if this one is before there's the edge from this to this, then this must be done before this. And that's exactly topological sorting.
Okay. But then, okay.
I mean, there
Right.
can be many topological sorts, by the way. We just told you that you can achieve one topological sort using DFS. There can be many topological sorts.
Right.
Right.
Okay.
I mean, you can do it in the reverse level in the sense that you can first do all the leaf nodes.
Yes, sir, but then I was asking where we're looking at all the leaf nodes.
Yes.
There the number of nodes are not M, right? There the number of nodes are N. We're looking at calculating every
not-
single value.
So not leaf nodes of this thing. So that's exactly why I wanted to make this distinction. Okay. When you are not thinking of the tree,
Right.
then you apply this DP kind of stuff where you don't think which can be calculated, which needs to be calculated. Okay,
Sir,
you
but
solve them one by one and you get filled completely. Now, to optimize it, if you want to optimize it further, then the idea is to first create this tree.
Right.
Okay. Once you create this tree, then the number of leaves are not all of them. I am talking about leaf of this node, this tree.
Okay.
Okay. Number of leaves of this tree is m, which can be lesser than n.
Right. So I was saying that any recursion is intrinsically calling some tree, right?
It is calling a tree. It is calling some tree, no doubt.
It is calling some tree. So this is the real tree that it's calling. But there in the DP sense, we are
Yes.
just saying that there is some tree or there is some forest. Actually,
Yes.
it's not really a tree, it's a forest.
Hmm.
And we know a good property of that forest is that anything before any node before another one in this array has to be
Right.
a
Right,
child
right.
node, or it has to
Correct.
come before
Yeah,
that
that's
in the topological order. Okay?
Yeah.
Okay, right, got it. Okay.
Any other questions? I mean, it's good that you are asking these questions because these are, so this shows that you guys are thinking about this. Yeah.
So, sir, here I can add this one more comment also that,
Yeah.
like usually when we are writing actual programs to implement problems, then recursion codes are actually very simple to write. So, if there is not a lot of, if there is not a difference between a DP implementation and the recursion implementation, just adding one or two lines in that recursion code will actually produce a quite efficient algorithm to do a certain
Correct.
computing event. So in that sense, sometimes like usually when we write, so the problem was that problem was given as a working code. So I'm guessing that is, but I know a lot of times, like if we can tweak the recursion, just one or two lines add, and then it just becomes quite efficient. May not, like if it is even close to DP, then writing it is very simple. That is what I'm
That
trying
is
to
true. That is true. I mean, the only difference between a proper recursion and DP is storing,
Yes, sir.
and that's it.
Yes, sir.
But again, you have to do it problem by problem because there are times when actually you don't need to store also. And there are places where simple recursion is faster than DP.
That depends again on the M and N discrepancy.
Yeah, I mean, like you might not want to store them. You can just pass on the whole thing.
Okay. Right. Which means something like some function. So like in the matrix sense, one row is only a function of the previous row. Then we only need to keep track of two rows.
Yeah, or simple the algorithm that we did for, say, finding the GCD. Right.
So CCD was
GCD.
Okay.
It's n comma d, right? GCD of n comma d is equals to. Sorry.
So are we talking about the greatest common divisor?
Yeah. Right. So this is nothing but GCD of d comma k, where k equals to. So k equals to n divided by, the remainder of k of
n minus lambda times d. So
alpha times d plus k. Right. So this is just a recursion. You call it. You said I am giving nd. I am just going to find out k, and I'll call GCD of d comma k. I don't need to store it. So storing it might take more time.
Okay.
Why to even waste space in storing?
Right. Here, actually, m is much lesser than n. Here, m is actually much lesser than n.
Yes. I mean, it depends upon,
because the tree that is generated from n comma d is much less dense
smaller
than the full tree. Right.
Good. Any other comments, questions?
Sir, I had one more. In one of the assignments, we had a question on the beakers, which was 10.7.5. There was a question with the beakers of some volume 10.7.5. Right. And we had to achieve a configuration which had 2 in one of those, of the 2 beakers. So was that an NP hard problem?
No. That's a reachability problem. I mean, particularly if you, no, it's not an NP problem. No. Yeah. Anyways, what is an NP problem? I'll talk about it later. So I don't want to discuss that one now.
Okay.
Yeah.
So if we can just touch upon this, was there anything better we could do rather than to make the vertices as configurations and then just do a BFS?
You can, by not doing the graph, drawing the graph to begin
So we won't draw the graph. We just know the neighborhood of every single vertex. So we
Yeah,
don't
so-
actually have to draw the graph.
Yeah, so in that case, you will be, no, that, yeah. So that's all that we need. That's
So,
all.
but then running BFS will still take linear time in the number of vertices in the abstract graph, right? In the worst case.
No, not exactly. In the words, no, it's not in the words. In the inputs, so depending on the input, whether it can be reachable or not, right? You can come up with a distance that, okay, if at all it is reachable within this much time. So your algorithm should stop after some time.
So we're saying that we should be able to figure out a distance from this reachable, from this
From the-
destination set.
Yes.
We can just say that this tree does not have.
If there exists, if a vertex is reached, it has to be reached within this much step.
Oh, so we could achieve that.
Yes, yes.
Bound.
I mean, at upper bound of it.
Okay. And that was not exponential.
Yeah.
Okay.
Okay. Any other questions? So I think there is a problem set that has been given about the MST and all those things, and there are some assignments have already been given, and so I will be doing today is something that I have started last class, and I will try to explain you guys this concept of P, NP, and various such stuffs. Okay. But next class, which is on Thursday, actually I will not be taking it. It will be so the tutorial will be on that day. Okay, so the TAs will take it and they will discuss more about problem solving and all those things. The tutorial class on Friday will instead be used as a proper class. So we'll have a next class, proper class will be on Friday at 5 o'clock. Okay. So, so let's see. Yeah.
Thursday class will be 1 hour and the Friday one will be 2 hours.
Thursday class will be, I think, think of something like that. Say 1 hour, half an hour, whatever. I mean, they will be there to discuss with you guys. If you guys want to ask more questions, they will be present.
And sir, what about the Friday one?
Friday one, it will be say around. Think of it as 2 hours only. So you have a class till 5 o'clock or till 4 o'clock?
Till
on
4
Friday?
o'clock. Yeah.
You have a class till 4 o'clock, right? So is it fine if I go for say another 1.5 hours or so after from 5?
So that's hard to say for everybody.
Yes, I understand that. But anyway, I will not be. It will not be too intense and not too long.
Okay. Sir.
Okay. So, so in the last class, I kind of discussed with you the class of what we call P. Okay, so it's polynomial time. Now, in the last class, I also discussed you how we can think of a problem as a language. Okay. So, but I will not be going that details in this class, but let me just think of that any problem. So any problem, but I will write it, any decision problem. Okay. What is a kind of function you can think of from the instance. What is an instance? So instance is an alpha. It's a kind of a sigma star, meaning it's a map from whatever has been given as an input. So sigma star is a string. You can think of the problem has been given to 0, 1. Okay, either true or false kind of stuff. Right. So any decision problem is this. So before I go into this formal definition of P again, let me give you some examples. Okay, so let me start with an example. Say I give you so the input. So So input is say a number n, and output is 1 if n is prime. Okay, so maybe this is a problem 1. So what is an input? Therefore, I can think of, so this input I can think of, this is a string of 0, 1 to start something. It's written in a binary, it is in a binary script. If you want to write it, if you want to say, no, I'm not happy with the binary, I am only interested in 0, 1 on decimals, that's also fine, perfectly fine. You can think of that. And the output is 1 if the number n is prime. Any problem with this? Hello?
No, sir. It's
No.
fine.
No, sir.
So let's think of another problem. Okay. So say I give you a graph G. Okay, and I ask, and the question, so so this is the input. Sorry, I should write it here. So input is a graph G, and the output is 1 if there exists a matching of size greater than or equal to k. Now, what does the matching of size greater than or equal to k meaning? I have a graph and I can give you a matching which has k number of edges like this. I mean, so that means there exists. So if this graph equals to v comma e, that means there exists an edge set. So e1 to ek subset of edges such that basically the ei is a disjoint pairwise. Ei ej is empty. Fine. So what is this? Again, the input. I can think of the input as a square matrix, right? So it will be 0, 1 to the power again star. I mean, if you want to think of it as a v square, but basically it's a I can think of it as a the adjacency list of the metric graph. Sorry, just the matrix of the graph. If you want to talk about the adjacency list, I can think of this to be equals to, so there are these vertices. So each of the vertex can be has a label, has some labels, right? So this is v1 to vn to the power star. Now this v1 to vn are labels of this graph. So I can think them as, I can think that this say each of these labels are just v1 is basically 1 and v2 is 1 and so on. So I can think of this to be n to the power star. Okay, so you can think of the input as some string that has been given as an input, and the output is 1 if something satisfied, the string satisfies something. Now you can say that what happens if you have given me a number, input, and that is not even a graph, then what should you output?
0.
No, it's output 0. It's an invalid input, right? So we are not interested in that setting. I mean, that's output is 0. Basically.
So,
Yeah. Yeah.
so could you just repeat how this is, how you're representing it in n star?
Okay, so think of these vertices. The vertices are labeled by integers. Okay. So I have the vertices are the v1 to vn are the vertices. I can think of it as these are the vertices is 1 to n. Right. So each vertex is 1 to n. Right. The vertices. Now, in that case, how will I write? How will I write the adjacency list of this? So I can think of that I will write is that I will first write a number. So think of it. How will I represent this whole thing as the graph and encode it? Okay. So I will first write a number n. This n determines the number of vertices that are there. Then the next one is the number 1, is vertex 1. Then I will write down the set of all at so then I will write the same, so not 1. And I will write the value of d1, so the degree of the vertex 1. Then I'll write degree 1 number of numbers that represent that are the neighbors of the first vertex. Then I'll write degree 2 and so on, right? So you can encode the graph like this.
Right, got it.
And there are many ways of encoding it. So there's no particular non-trivial things here. Fine. The encoding part is not the fun part of it. Okay. Now let's see some other problems. Say I have given you a set. So input. This is a set S of S1 to Sn of these are all subsets of the subset of n, and a number I have been given d, and the output is if there exists a subset S prime of S such that the summation of Si's in S prime, just 1 second. Hello. Hello, you're there? Hello,
Yes,
can you hear me? Yeah.
Yes, sir.
So the idea is that if there is a if there exists a subset of S, such that the summation is exactly t. Okay. Fine.
yes, sir.
Now, so this is problem 2, problem 3, it will be. I can write another problem, say. Okay. Say that I'll give you again the input is say a graph G, and the output is what? Output is 1 if and only if there is a vertex set, vertex cover of size less than or equal to say k. So this is a k involved here. Did I write a k here? Okay, I should have written a k over here. This k is also an input. Okay. Now what is this? What is the vertex cover? So a vertex cover is a subset v prime of v such that for all u v in the H set, okay, either u or v must be in v prime. So u comma v intersection v prime is not equal to empty. Okay. Now let me give you another problem. Now this problem is very interesting. That I'm sure this problem that you guys have seen in many or you have thought about or played something. So what is the input? So the input is a configuration of a chess game. Of a chess board. So they have, so two players have played, and at some point of time we have a configuration of the chessboard. Okay. Now output is one if there exists a winning strategy for the black piece. So question is that does the black have a winning strategy? So what does it mean? That is there a strategy that black plays some way in which in any way the white plays, the black will always win. Is this problem clear?
Yes, sir.
For
Yes,
all
sir.
of you? Yeah.
Yes, sir.
Yes,
So
sir.
we have say a collection of say 5 problems that we have got. Now let's try to understand these 5 problems. Okay. First of all, what is it that, what would you like to do with these problems? Okay. Yes, the first thing that you like to do is solve them. Right? So given the instance, you're given any instance, can you solve it? Okay. And that is what an algorithm is, right? An algorithm will nothing but an A that will take in an input as an instance I and will output the correct answer. Right, so that's an algorithm. So if I draw it in a nice picturesque way, you put in an input and it has output 1 or 0. Right. So this is a solving of the problem. Solving of the problem. Now, what do I want? I want my algorithm to be good, to be fast, right? The number of steps to be small. Okay. And this is where you can, what we kind of talked about is that P, this is the set of all problems L. Now, why do I define that as? Okay, so L, so all these problems are problems. Okay, so you can, so if you guys remember it, or I can define it. So given a language here, right? So the input is plus minus 0, 1 to the n start. So they are all strings of length, various lengths of 0, 1 to the n. So what is the language corresponding to this? Can somebody say the language corresponding to this? So language is the set of all words or set of all strings or set of all inputs which evaluates to 1. Okay, so the language is nothing but the set of all primes, right?
Yes, sir.
Okay. So what we are trying to answer is, you are given an instance X and I'm asking, is X in L? So in some sense, maybe I should, before I define all of these things, so maybe forget all of this stuff. Okay, for a problem from sigma star to 0, 1, the language L is the, so if I say this is the problem P, it is the P inverse of 1. Now this is the set of all x's such that P of x equals to 1. Okay. And so a problem is nothing but an input. What is the input? Input is an X, which is in sigma star, and the output is 1 if and only if X is in L. Is this fine? Are you guys comfortable with this notation?
Yes, sir.
Yes, sir. Yeah, so if you're not fine, please shout out, okay? Because I know these are a bit abstract, but I mean, I expect you guys to follow it. But what we are doing here, or what I'm doing here, is doing a part of this course called theory of computation. So in many places, theory of computation is done as a separate course of 2 algorithms. But because here in your undergrad, you don't have theory of computation as a separate course, so I have to define a little bit of it here. And without doing that, we will not be able to define these classes of P, NP, and so on. Okay. Now, okay. So now once you have this thing, I can define this set of all languages. Okay, what is P? So P is the set of all languages such that, okay, what is it? That such that okay, there exists a polynomial, say Q, okay, such that for all X, such that there is a polynomial Q and there exists an algorithm A such that for all X, if you take X, A of X equals to 1 if and only if X is in L, so it outputs correctly, and the number of steps of AX, so A on X, this is less than the polynomial with the so it's upper bounded by a polynomial of the size of the X, the input X. So these are all the problems for which there is an algorithm that in worst case, so that means for any input X of size some R or any R, there is an algorithm that solves that problem or answers it correctly when the number of steps is less than a fixed polynomial of this size, input size. Is it fine?
Yes, sir.
Yes, sir.
Okay, good.
Sir.
Yeah. Yeah.
Sir, this L is for only one problem, right?
This is a set of all languages L. So the A, of course, depend on L. Q also depends on L, if you want to think of it. This N meaning, is it fine?
So really scroll a bit up. Just
So for example, let's say this problem, right? Say this problem. So I say that, oh, this problem, I have an algorithm, polytime algorithm, meaning give me any graph and a K, I will solve this problem in polynomial time, polynomial in input size. That means this language, the L corresponding to this language is in P. Or in other words, this problem is in P. If I tell you that, oh, give me any number, I will check whether the number is prime or not in polynomial time, polynomial in the size of the input. That means that this language is in P. And we kind of use it as saying that the problem is in P.
Yes, sir, it is clear now.
Okay, so P is the set of all problems for which we have a polynomial time algorithm. Now, maybe some of you are asking me that what is an algorithm? Is anybody who's asking me that? And am I thinking too much?
Sir, I am.
You are? What's
I
your
am
name?
also asking how do you count Sir Arunabhu?
Yeah.
Sir,
Yes.
I am also asking how do you count the number of steps?
How do you count the number of steps? Okay. So now this part I am not going to explain. Okay. Now the reason I am not going to explain is that, so you are asking a very good point. Okay. Particularly if you come from a mathematician's point of view, a formal definition is required. What is an algorithm? What does it mean by number of steps? Okay. Now, this question was first asked by Hilbert. Okay. And how do you define computation? How do you define solving a problem? How do you define an algorithm? What kind of questions are solvable? What can be solved? What cannot be solved? Can all questions be solved? So you have lots and lots of these questions up there. Okay. So this question, so what is an algorithm? What is number of steps? Does every problem have an algorithm? So now these questions are all forms under, so these are all of them questions that are asked by Hilbert. And this is what was one of the main area of research in the early 1900s, between 1900 to 19. So I think in 1905, Hilbert asked this set of questions. And these things you possibly know them. So there are a formal definition of an algorithm was described. Okay. Now this is where things are a bit vague. So we have a model, what is called that anything that can be solved by this model is an algorithm. Or any operation by this model is an algorithm. Okay. There are other ways of defining it. Okay. Also, so that model or that machine, if you want, is known as the Turing machine. Okay. So Turing machine is not a machine. It is a abstract machine. Okay, it's an abstract machine you can think of, or abstract logical step-by-step operation. Okay. I don't want to go and get distracted when trying to explain you what a Turing machine is. I will let you guys go and read it off by yourself. But basically the idea is that if you take a pen and paper with an infinite amount of paper, and if you start writing steps one after another, okay, but every step follows from the previous step, then you keep on deducing, and at the end of the day, you will get an answer from which you can decide whether you have solved the problem or not. Just like you do it in any proof of any mathematical statements and all, right? So that thing, if you can think of it abstractly defined, that is a Turing machine. A Turing machine basically says that. Okay. Now Turing machine, Turing machines are what we can call as our algorithms. And there is something called a Church-Turing thesis. Now, I should say this is not an theorem. Church-Turing thesis. This basically says that any problem that has a solution can be solved by a Turing machine. Now, this goes into a very complicated discussions about what do that mean. Are there problems that cannot be solved by this solution? You might have heard things of Gödel's incompleteness theorem.
Yes, sir.
Yeah, they also fall in the same genre. Okay, so does every problem has an algorithm? This is so answered by Gödel's incompleteness theorem. Now, question is that, so once you have that, so Gödel proves that no, not every problem has a solution. He proved it. And if you are not familiar with the proof, I recently found out a very nice video on that. And I can just maybe put the link of that video in the web page if you guys are interested in knowing the proof of that. So he proves that not every problem has a solution. So it doesn't mean that it has a right solution. It doesn't have a solution. It means you cannot prove that statement or disprove that statement. Okay. So that's what we mean by solution. Now the question is that, okay, then which all problems has a solution? What is the set of problems or statements for which we know a solution, whether we can give a proof? Okay. And then the whole thing comes up, what is the proof? And that leads to this whole thing of Church-Turing thesis. Now, what is the Church comes in? So there's a guy called Church who came up with a definition of what is a solution using a completely different technique, which is called lambda calculus.
Lambda calculus.
Yeah. And what they managed to prove is that the class of all problems that they were describing, that lambda calculus was describing, that can be solved, and the class of all problems that Turing machine could solve, they two are same, identically same. So here there are two completely different view of the world, okay, that the different classification of problems that can be solved, that can be defined as, so this is used to define this set of problems that can be solved. Now, this is not a thesis, theorem. So, a theorem, the theorem part of this is that the Church's part and Turing's part are same. That's the theorem. But the fact that these two, that the set of all problems that can be solved and set of all problems solved by Turing machine or a Church's calculus are same, that is a not proven thing. Because this is the model. This is a fact. You cannot prove this too. And this too has been, at various point of time, been challenged. One of the big challenge came from Feynman, who kind of introduced the concept of quantum computing. And he argued that, is it possible that you can have problems that using quantum computation things can be solved, but not using classical computation? And this whole thing has to be revisited and all of that, and then it was called the extended Church-Turing thesis and so on. So if you guys are interested, I'll be happy to connect you to all of these things. But unfortunately enough, for this algorithms course, you have to live with a very high level description of what an algorithm is. Okay. I don't want to go into the formal stuff. I just want to say that all of these statements that I'm making has a formal background. You can make all of these statements very formalized, all of them. And these are beautiful, really beautiful. Okay. I just wanted to give you a quick set of links to various things that if you want, you might want to study by yourself. So whatever I told about this, what is an algorithm part, if you are not interested, forget that. Okay, don't have to worry about it. But
Sir, how much of P and NP do we have in the syllabus?
we have P and NP. Okay, we will come to that. I mean,
Sir,
why? What happened?
No, I mean, so do we have things like proving whether a problem is in P or in NP, something stuff like
Oh,
that?
yeah, of course. Of
Oh,
course,
so-
that is
okay.
there. Yeah, yeah. Proving a problem is in P. What is the problem? I have not even described it in P. So that's a wait for that.
Oh, okay, sir.
I have not defined NP. I have just defined you P. Okay. P is easy to describe. Okay, because P is a set of all languages or all problems that you can solve in polynomial time. You can give me a polynomial time algorithm. Now, for example, think here. Let's go by one. Do you think this first problem has a polynomial time algorithm? Does this have a polynomial time algorithm? Or can you give me one polynomial time algorithm?
So we can just keep on checking from 1 to n.
You keep on checking from 1 to n whether they divide it or not.
Right.
Right? Is it polynomial time?
So no, it's not polynomial time
Why not?
because the input should be log n.
The input size is log n. Very good. So
Okay.
input size is log n. You are doing n steps. So the number of steps that you are doing is exponential in n. Exponential in input size. So the algorithm that you gave me is not in polynomial time. That doesn't mean that this cannot be done in polynomial time. It's just that you have not been able to give me an algorithm in polynomial time. Okay.
Sir, will you kindly explain why it is not?
So,
So if so, yeah, go ahead. I mean, maybe I'll explain this one. Yeah. So tell me, Anurag.
so if we try to shorten the number of things that we have to check, then I guess we can achieve something better. So
You can think about it. Okay. I'll come back to that.
okay.
So, so the previous algorithm that was told, what was it? That if you want to check a number is prime or not, okay, you go over all the numbers between 1 and n, or say 1 and square root n, if you want to use it, or 2 and square root n, rather, and check whether that number divides that number n or not. If it divides, then you know that the number n is not a prime. And if it divides, then you know that number n doesn't have a factor of less than square root n. Right? And if a number doesn't have a factor of less than square root n, then it must be prime. Now
Sir,
the issue, yeah.
if your alphabet is 0 to 9 star, then yes, this is a polynomial time algorithm, right?
No, why?
Because the input size is the decimal size and it's polynomial in that. And it's root over
What
n.
is the input size? Okay, let me give you this one. Okay. So this primes, okay. So let me go down.
Oh, no, sorry.
Yeah, you have the primes, right? Now I'll give you a number 21765291003. No, I don't know what all things are there. 1, something like that. Is this number prime? Now, what do? I mean, at most standard or simple problem is that for I equals to 2 to square root of this quantity, whatever that is, let's call this n. And if n, so if I divides n, then output 0. Right? Else output 1. Now this is an algorithm, and there's no doubt this is an algorithm. There's no question about that.
So
But-
there will be no else.
And not else, but I mean, basically, I mean, if you don't output anything, then you output 1. Okay.
So there has to be an argument which shows that this is the best we can do, right?
Yeah. First of all, I'm saying that this is an algorithm, right?
Right.
It's the correct algorithm. This algorithm will output the correct thing. There's no doubt about that, right?
Yes, sir.
The question is that how many steps this algorithm take. So the number of steps is
Square root n.
Exponential.
square root n, but the input size is what? This is the size of the, when I say size of n, meaning a size of n as this one. So this is basically log base 10 of n. Right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So actually in this case it is 11.
Yes, sir.
But the square root 10, this is 2 to the power or some c to the power,
10 to the power 11 and
Yeah.
divided by 2.
right?
Yes.
So it's an exponential in the input size.
Right.
So this algorithm is not known to be, is not polynomial. But that doesn't mean that this algorithm is not, that there is no other algorithm that is polynomial. You guys know of other things also, by the way. You know the Fermat's little theorem and all those things, right?
Yes, sir.
So you can check
Yes,
those
sir.
things. If it is a prime, it should satisfy all of that thing. But do that make it if and only if? That's not true.
No, sir.
Right.
No, sir.
There we can get lucky with some of them.
You can get lucky with some of them, you might not get lucky.
Right.
But maybe if you
Sir,
make a
they
lot
are
of
all the
this.
Carmichael numbers, right?
Sorry.
So the non-primes which satisfy Fermat's little theorem are the Carmichael numbers.
Yes, it can be the Carmichael numbers. Right. So how we'll know that? There may be other things like that.
Sir, so you're saying that if we're looking at the set of all those primes which are which we can find with the Fermat's little theorem, and
Hmm.
if we can just break up the set of all primes into
Right.
smaller sets which can be found out by one of these things, then maybe we can do something better. That is-
Maybe you can do it. I'm not giving you an algorithm. I'm just telling you that there are other possibilities other than the most obvious algorithm.
okay, right.
Okay. And in fact, one of the very big results to come out of India in computer science in the last maybe 50, 100 years, maybe forever almost, is that this is a work in 2002, Manindra Agarwal, Nitin Saxena, and Neeraj Kayal. Actually, it should be, I made a mistake here. It is Kayal, Neeraj Kayal, and Nitin Saxena. So actually, Kayal and Saxena were both undergrads at that time, and Manindra Agarwal was already a professor. And they proved that this is called primes. So the primes is this language, okay? So this language is in. It's one of the great works that has come out in. You might have heard of it. It's called primes in P. So
What it is called? Prime?
primes in P.
Oh, okay.
And the algorithm is not at all complicated. I am not going to do it in this course. But if you guys are interested, with a little bit of number theory, you will be able to solve it. Okay. So this shows that there are problems that by first sight doesn't look like they're in P, but they can very well be in P. Okay. Okay, good. So these are the ones kind of stuff. Now, okay, let's go back to the set of problems once again. So see, there are these problems. Now, similarly, I can ask about this matching. You can think about this matching problem. Is this problem in P? You can think about this problem. Is this in P? You can think of this problem. Is this in P? And so on. Or the graph problem. Is this in P? No, sorry, in the case problem. Now, if you can come up, yeah.
So in the graph, the input size is V plus E, right?
V
Even
plus
in
E.
this sense.
Yes, even see again, when we're talking about polynomials and non-polynomials, then V plus E and V squared doesn't matter that much. So you can think of them as, if you want to think of it as, you can think of them as adjacency matrix also.
Okay, right.
Because V and V square are just polynomial of each other, right?
Right, right.
So how much does that matter?
Right. Okay.
Now, sadly enough, many of the problems that we are actually interested in solving in real life, they are not in P, or we have not been able to prove them in P. Okay. Say a good example is, say, this problem. This is a very important problem. Okay. This is called a subset sum. I have given you a sum, a set, and I have a set of set, and I have a number D, and asking, is there a subset of size D? Now, what is it that you will do? What is an algorithm that you will do? A standard example is that, okay, let's try to maybe write it as look at all the possible subsets, but that's 2 to the power n. Or you might think that, okay, can I kind of model it as a graph and solve it? Go ahead and try to solve it. Let's see what happens. So this problem, we don't know it is in P or not. But this is a problem that we are very much interested in solving. This is required in various computations. No. But these problems have another interesting fact. So what happens, say, you are trying to solve this problem. You have an instance and you are trying to solve this problem. Your friend comes up and says that, yes, the answer is 1. So there exists a subset. And you don't believe your friend. Then what can you do?
So you ask them to provide that subset.
You ask them to provide a subset. You can ask your friend to prove me. I'm not an idiot. I know how to solve. I am a polynomial time machine. I have limited time. You have managed to solve a very hard problem. Fine. But you tell me now, for this instance, how is it D? And what will your friend do? Your friend will provide you this subset. So see, here is a subset. And then what do you have to check? Whether your friend is lying or not? All you have to check is that whether the subset is actually a subset of what set that you have, and whether the sum of these elements in subset is D or not. So this is a case where possibly if you are a polynomial time machine, if you have a machine that can only be running in polynomial time, it is not able to solve this problem. But if somebody comes up with a solution and says yes, then you can verify its answer. Or there is a way to verify its answer. So similarly here, okay, you have a graph and you want to check one if the there exists a vertex cover of size k. You possibly don't know how to solve it, but your friend comes up saying that yes, the answer for the graph that you have is yes, 1. Then what kind of proof that can your friend give you?
They can provide a vertex cover of size s is equal to k.
They can give you the vertex cover v prime. All you have to check is that actually is the vertex cover of less than size k, and whether this is actually a vertex cover. Is this condition satisfied? Now, checking whether this condition is satisfied or not, that can be done in polynomial time, because all you have to check is for all uv whether this is true or not.
So what if the friend said no? The answer is no.
I didn't say anything about that. Okay, so that's where the difference comes in. So it is not a full answer. Okay, so I will tell you what happens in the case of no, but this is called the NP. It's a non-deterministic polynomial time. So what is it? This is the set of all languages such that, now remember, in the case of polynomial P, it was the set of all languages that had an algorithm that can be solved in this time, right? Good. So here it is also the same thing, okay? Set of all languages such that there exists a polynomial Q and an algorithm A such that for all x, okay, now here is the interesting part. Note that the algorithm's job is not to check, it's not to find out the solution. Okay, so if x is in L, so if the answer is yes, then there exists a y, okay, so the size of y is less than, so maybe I can write it as and the c also, size of x to the power c. So there is a polynomial sized witness that can give, okay, such that a on x and y is 1 if and only if x is in L. Now let's think a little bit more here. Oh, and a runs in time q of size of x. Okay, so basically it says that if x is in the language, that means if the instance satisfies the instance, if the graph has a vertex cover of size less than k, or if there exists a subset that adds up to d, then there exists a what we call this one as a witness. There is a witness of size polynomial in the input size. It's not a huge polynomial, it's huge witness, it's a short witness. Okay, so this is the witness of the size of the subset of the set that adds up to d, or these things that are the vertex cover itself, such that the algorithm, what will the algorithm do? The algorithm will take x, take y, okay, and check. Oh, okay, good. You have given me the right answer. So this is equals to 1 if and only if x is in L. So the algorithm cannot be fooled. Okay. So one way of saying it is that, as I told you last class, it's the teacher and student solution. Okay. I have given you a problem to solve. Your job is to solve it. I can check whether the solution is correct or wrong. So I am the A, the teacher. Okay, I have an algorithm to check. Your job is to come up and give me a proof. And I'll check whether it is correct or wrong. Now, just because you have not been able to give me a correct answer doesn't mean that the proof, there doesn't exist a full proof, a correct proof. All I'm checking is, yes, is there a answer or not, correct answer or not. Another example that is used is like, say, so I have a king Akbar and a advisor Birbal. Okay, so Akbar is smart, but not very smart, and Birbal is an advisor. He is very smart but can sometimes cheat, can make fool of things. So Akbar has a problem to solve. Birbal says that yes, I have a solution. Now Akbar doesn't have the smartness to come up with a solution. But given that Birbal can give a solution, if Birbal gives a solution, Akbar is smart enough to check whether that solution is actually a solution or not. So set of problems that Birbal can solve and convince Akbar that yes, that problem has a solution is the set of NP. Okay, how this in Y comes up is not our job, but there exists a Y. Okay. Any questions? How confused are you guys with this notation?
Sir, won't it be Q mod of Y? Because we are checking for mod Y, right?
You can change it to Y, you can change it to X, doesn't matter, right? Because there's a C over here, which is also the Q is, I mean, Y is of size X to the power C, anyways.
Means Y is given by my friend, right?
The actual input is X. The Y is given by your friend. The size of Y is bounded by a polynomial in X.
Yes, sir.
Okay, and the algorithm runs. I mean, if you want, you can add it over here also, Q of X comma Y, but they're same. I mean, you have a different Q for that matter. See, there exists a Q, right? That's all I'm saying.
So in the case of the graph problem, what is the Y?
In the case of the graph problem, tell me what is the Y?
Y is the list of vertices that vertex cover.
Yes, Y is the list of vertices in the vertex cover. Okay, note that, yeah, is it fine? Is it clear? Hello.
Yes, sir.
So here is the list of vertices. What about say this one? This matching thing. Matching thing?
The list of matches.
The list of matchings, right? What about here in primes?
The factors.
Aha, now think about it. Is it the factors?
Oh, the fact, no.
So here
In-
we'll have to devise the transpose problem, right?
Right. The complement problem.
Right.
Or the set of all non-primes. That one witness is a set of factors. Is a factor. So your friend is trying to convince you that thing is prime. How will he convince you? If he convinces you that there is a factor, that doesn't solve the problem. So he convinced you the other side. Okay, so this also comes to this thing that what we just described here, as somebody else pointed out, that why are we just interested in the case of if and only if, so this thing, if X is in L, only then I'm saying that such a thing is exist. What happens if X is not in L? Then So for example, here in this graph problem, if there doesn't exist a vertex cover, how will you tell everyone? How will you convince everybody?
So we won't.
I mean, at least it's not obvious. How will you convince, right?
Right.
I mean, maybe there is a way of convincing. We don't know. But it's not
Yes.
obvious at all.
So in problem 1, is it the number of factors of that number?
So your friend is trying to convince you that a number is prime. Then what will you convince? How will you convince
It's
you?
a number of factor of that number. If it is 2, then we are done.
How will you check whether, so since as your friend has said that it has only 2 factors, 1 and n itself. It doesn't have
Then
any
it's
factors.
prime. So it's 1.
Yes, but then how will you check whether your friend is cheating you or not?
In polynomial time.
In polynomial time, how will you check that? Your
So
friend
that
can
just
cheat.
becomes
Oh, that's
I ask for the factor and then I divide the factor. I divide the number with the factor. If it doesn't divide, then it's prime.
That's true. But if the factor is, yeah, but if the number, so I have given you a number, okay? Say 197. I have to convince you that 197 is a prime. How will I convince you?
Oh,
It doesn't have a factor, prime factor. It doesn't have a factor other than 1 and 197, right?
so it's even hard to show that this is an NP problem. Not even-
This is very hard to show that this is an NP problem, sir.
Right.
Okay. So by the way, just this thing that I defined here. Okay.
So we want
So
to
this
show-
whole thing, I defined this NP as like this, right?
Yes, sir.
Bad job. I defined this NP as this thing, right? Now, if I just, I'll make a copy of this. Just one second. Okay, if I just have just changed it a little bit, and I say that if x is not in L, then this is the case, and if x is 0, if and only if x is not in. I just made the flip of this whole thing. So now the only difference is that if somebody says that no, see, you're trying to prove that x is prime, but I mean, your friend is just trying to prove that x is not a prime. That's all that is proof. Then this is called a co-NP. It is just the opposite of that. So in that respect, you can say that primes that you have seen is in co-NP, because if it is, so co-NP, the friend has to convince you that that instance is not in the language. Okay, so in this case, the friend has to convince you that the input is a composite number. And what instance can he give? He can give a
non-unit
factor. Yes, he can give a non-trivial factor of that. And I can check. Okay. So we had this vertex cover that was in NP. We had the matching that was in NP. We had the, what is the other thing, that is subset sum that is in NP. What about chase? Where is it
Sir,
gone?
we cannot even check it in polynomial time.
We cannot even check it. We can do something even worse than that. In this case, okay, what is the instance? The instance is the 64 set points, right? A constant size object. That's it.
So 64 plus the pieces and their position.
Yes, sir. You have to
Yes, and the
prove where
position.
pieces are, right?
Yes, so there are 16 pieces or whatever, 16 different pieces, right?
32.
Actually, you don't even have to have 32. You can have all of them, all the pawns are same, right? All the
Yes.
pawns are same, all the rooks are same, and all those things. The total number of distinct pieces of distinct colors, of other
No,
colors.
sir, but you need this their individual positions. No, so it is still 32 positions.
Think about it. Yeah, okay, that is also, you can do it also like that. Okay, fine. Let's do it at 32. Okay, so that is another thing. So 32, you have given 32 positions. So 32 into log of 64 kind of stuff. Okay, whatever. It's a constant. You can describe the whole of the any case configuration in constant number of steps, right?
Yes, sir.
Yes, sir.
Now, is there any guarantee that this whole input will stop in constant number of times? That the winning strategy itself is a game that will take less than a constant number of possibilities or polynomial number of possibilities, let's say.
So there is an upper bound, but
That is
it
exponential,
right. It is exponential.
right? The upper bound is exponential. So it's not even clear if somebody tried to convince you, okay, the total tree structure that is there. So I have in a particular configuration, I can play this move, I can play this move, and so on. Then that is what white black will play. Then the white will play some other moves, various places. You have to prove that any of these moves leads to black's winning. Or basically, for every moves of white, you can have a move of black that will finally give black the winning.
Sir, it should not also belongs to co-NP, right?
It is not even in co-NP. At least not clear at all, right? I mean, we are not saying that whether it belongs or not, but let's put it this way. We cannot show it to be in NP or in co-NP.
So CoNP, hello?
Yeah.
Yeah, so CoNP are the problems for which you can produce polynomial size proof for the no answers.
For the no answers, yes. So here the no answer would be that in this configuration, black cannot win.
Yes.
Okay. So we have this huge diverse things. By the way, I also proved to you that, see, actually, although this is what we could show right now, primes is actually, I have a polytime algorithm. So note what happens here. What about P versus NP? If I have a problem for which I know how to solve it, right? I know how to solve it, whether X is in L or not, in constant amount of time. Sorry, in polynomial amount of time. I know how to solve it completely. Then I don't need any configuration, any witness from my friend, right? I can take X, I solve the problem and done. I don't need a witness from my friend either for X is in L or from X not in L. Right?
Sure. So every P problem will be NP as well as co-NP.
Exactly. So any P problem is in NP, any P problem is in ONP. So the picture that is described usually is what is looked as this one. Okay, this is NP, this is ONP. So these are the all, and there is a set here which is P. You might see this picture in many books and many places. Okay. Now, the big question here. Is P equal to NP? Now, this is a big problem, and we don't know a solution. Okay, it's a big conjecture, or whichever. Some people say that P is equal to NP, some people say P equals not equal to NP, and so on. Okay. Now, while we don't know that P is equals to NP or not, okay, we know some more interesting things. Now, this is something that I will do it in the next class, which is on Friday. But basically, I can show you, okay, so this is where we will be going next, that there exist problems in NP that are the hardest problems. I have to write it. I have to kind of describe you what do I mean by the hardest problem. Okay, so this is what I will be trying to prove in the next class, or at least I don't think I will prove it exactly, but I'll at least give you the whole thing, because the proving will require some, again, going to Turing machines to some level. But there are problems of this form. Okay, so I will not solve it in this class. Okay, I let you guys to go back and think about it. I will try to, I will of course post this slides that I have, no slides or whatever notes in the classroom, not classroom, in the web page, and the and today's lecture video. I will upload it. In any of the algorithms book, you will find this section there. It's on P, NP, NP completeness, NP hardness, and so on and so forth. Okay, I have not completed the whole section, but it is a very important section. I will do it one by one, slowly. So now, I mean, maybe guys are a bit confused about why am I doing all these things in the middle of an algorithms course. So let me try to quickly tell you why am I doing it. Okay, so what have we done so far? So far in this course, what all things have you done? We have seen some basic problems, like say sorting, searching, maybe some kind of some we have seen some basic algorithmic techniques like greedy, like DP, recursion, cursive. We have also seen a little bit of this reduction. Okay, so of course we have this graph algorithms, some basic graph algorithms, right? Where I kind of model problems as a graph problems, and so on, right? So we have seen these three basic concepts. Now the important thing is that all of them that we have seen, they are all basically very nice, precise polynomial time algorithms. All of them are polynomial time algorithms. And all our goal was to improve the polynomial, right? So the idea was that, okay, can I do DFS in linear time? Or can I find the shortest path in quadratic time? Can we improve from the cubic time to quadratic time, and so on? So this is how much we have done in this course. But problem is that in real life, many problems are hard, meaning they are not in polynomial time. So at least we don't know how to prove them in polynomial time. Let's put it this way. So in fact, many of them in P. So if a problem is in NP but not in polynomial time, we don't know how to solve that problem, right? So how do you solve it? How do you go about it? How do you prove it? What do you work? How do you kind of, just because I don't know how to find a solution doesn't mean that I should stop at solving the problem. In fact, most of the important problems in the industry that is required nowadays, almost all of them are NP hard problems, or problems that are NP, which is the hardest problems in NP. So in the next few lectures that we have, we will be talking about this set of problems. And one of the most important concepts that you will see that is coming up is in this thing that was kind of less focused till now, is the reduction. So reduction, something that we have not gone that depth into it till now, is something that will come up in a big way. That you are given a problem, you reduce it to some other problem and solve it. It is impossible for anybody. So if in the industry or anywhere, if you try to solve a problem from beginning, it is impossible to solve it. It's too hard. So why not use something that has already been done to solve it? Okay. Particularly if the problems that we are talking about are so hard that you have to come up with some crazy algorithm to solve it. So this is where the reduction will come up in the very handy way. And then you will see that in the next few classes, some problems, some special problems will take center stage in this world. Some problems. So these are the problems that we will call NP complete problems, and more than that, we will be talking about a certain set of problems, particularly this called a satisfiability. Integer linear program, ILP. Some other problems like the vertex cover. So they will take the center stage of problems. Okay, and this is why unless we understand where we are, we will not be able to kind of appreciate what we are doing. So for the rest of, or for next 2-3 weeks, we will be using all these techniques that we have got, that we have seen so far in handling basic problems, the basic building blocks of algorithms, to solve problems for which we don't have polynomial time algorithms, and still try to do as much as we can. And so this is exactly where we are heading now. Okay, we will be coming back to some other basic problems a bit later, but for now, this is where we are. So I would like you guys to go back and again, as I tell you, go over this lecture notes, but more importantly, please read a book. Take any book and go over it as much as you can. This section or this chapter on P, NP, and those things. There are lots and lots of interesting things that I have left out. For example, Turing machines. For example, Gödel's incompleteness theorem, and so on and so forth. So for example, the thing that I talked about here there exist problems that are hard, I will not be able to give a formal proof of it unless we have a notion of Turing machine. Okay. And that is exactly the reason I will not be giving you a proof of it. I will kind of give you I will try to, without giving a proof, I will try to at least give you some more insights into it. But in the meantime, if you guys, whoever are interested, can read for yourself what a Turing machine is, I will be happy to discuss with you guys as much as we can, and we can see what can be done. I mean, I can even possibly take some extra course classes just for those people who are interested to prove these concepts. Okay. Now, I mean, the interesting thing is that while this big problem is in, as I told you, the big problem is P not equal to NP. Due to this, all of this thing, what it will turn out is that this problem, solving this problem, would just be same as solving is what subset sum in NP. Sorry. I mean, so I mean, this is something that I will show it, and I'm just trying to advertise it to some level, that P equals to NP question. This is equivalent to saying whether the vertex covered is in P. This will be same as saying whether subset sum is in P. Yeah, tell me.
All these problems are the hard problems that you're talking
Yes,
about.
so they're all the hard problems of NP, and so basically this whole problem is, can you solve this particular problem in P?
Okay. So even if one of the hard problems gets solved,
Then the whole thing will be done.
Okay. Like the knapsack problem was also mentioned.
Knapsack problem was also of one of the things. Yes. Okay, so I think I will stop here. It's 4 o'clock now. So
Sir?
Yeah.
Sir, I just wanted to ask before we end.
Yeah.
So could you just explain how that question in the assignment with the beakers, how we can talk about a polynomial?
Okay, so I have to go back and look at it completely properly. So maybe I will do it in the next class, or maybe you can ask the TAs and they can try to explain. Did you ask the TAs about that?
No, sir.
No, you should. Yeah, I don't remember the exact problem that was there.
Okay.
Yeah, but before I end, so how many people are there in the class today? Hello.
15.
15 people there in the class?
I mean, including you.
No, I mean in the class, meaning in the physical class.
Only one person.
Only one person. Okay. Okay, so so at least next week I will have one physical session sometime. I will let you know. Okay. Either the tutorials or the course and all, and let's see how it goes. So rest of you, are you guys planning to come back to the campus? Has they told anything about the NSEM or something?
Not yet, sir. Nothing about the answer.
So nothing about the NSEM, whether it will be physical or offline.
No.
So it's supposed to be offline. There's no other sub update regarding that.
So all of you are planning to come to the campus, I assume, right? In that
It's
case?
at some point.
Okay. Okay. So I'll see you on Friday, 5 o'clock. Okay.
Thank you, sir.
Thanks.